Terry, hello everybody. Welcome to the last day of AES 2019. Hope everybody's had a really good show, and I'd like to thank you all for spending some time with me here to talk a little bit about the wonderful world of AES70. So, my name is Ethan Wetzell. I work for Bosch Communications on platform technology as my day job. I'm also the marketing chairman for the OCA Alliance, a member of AIMS and numerous other trade associations. So, what we want to do today is spend a little bit of time talking about the other part of the wonderful world of media networking. Namely, we've spent all of this great time talking about different ways that we can move my content, my audio, my video from point A to point B on an integrated media network, but the question remains, what can I do with it when I get it there? So we still have this issue of how am I going to interface with my devices, my device parameters, turn things on, turn things off, make adjustments in real time with my overall devices. So when we look at the general media networking landscape, there's really two fundamental problems that we have to address when putting together a fully integrated solution. On the one hand, we need to be able to move our transport around, but on the other hand, we also need to be able to interact with our devices to get control over where we're actually sending our content. So there's a number of different solutions and technologies that are available today to deal with moving my content around. Could be any of the number of things that we've talked about here at this theater related to ST2110, AES67, other solutions that you may find around the show, such as Dante or Ravenna that Andres was just talking about. Of course, there's always good old-fashioned analog, or you may have situations where I'm not actually moving any content. I just need to have device control. Happily, we've worked on a solution with AES70 that can peacefully coexist alongside with any or all of these media networking transport solutions. So, why reinvent the wheel, right? There have been all sorts of different control protocols and solutions and standards that have been around for quite some time. When we began to work on this within the OCA Alliance back in 2011, one of the first things that we did was actually take a very comprehensive technical survey of the different technologies that were available within the industry. And while there were all sorts of really excellent solutions for their intended applications, we had slightly grander ambitions than any of those technologies were actually able to address in their entirety. So specifically, we needed to look for something that was oriented towards professional applications, high demand, high integrity, high reliability systems. We needed to be able to have a solution that would scale up to very, very large system sizes. Not just dozens of devices, but hundreds or thousands of devices with hundreds or thousands of parameters. Both large as far as sophistication, but also large numbers of device counts, and also potentially large geographic counts. We needed to be able to support high numbers of simultaneous and concurrent users, multiple controllers, multiple devices. So scalability was a really, really critical element that we needed to address. We also needed to make sure that we had high levels of reliability for mission-critical applications. So functionality that would ensure that the system can keep running, had high levels of reliability and functionality as the system is operating and as it's being used and configured. We also wanted to make sure that we were very friendly to proprietary product features. And this was a really big challenge because when you're developing a control standard, you need to sort of thread the needle between making something general enough that it can be applied to unique product features or unique parameters that exist within a device, but it needs to be tight enough that you still have some sort of standard object orientation that you can interact with and understand. So we spent a lot of time looking at how we build up some of the objects in the class trees to be able to support unique product features and proprietary functions in hardware when and if that's needed by a product. We also wanted to make sure that this was something that could be future-proof. So looking at not just the types of devices that we're controlling today, but what sort of devices are going to come tomorrow? What other application areas might we want to address? Audio, video, telemetry, control, any number of different things may need to be integrated into some of the systems that are going to be coming down the road. Additionally, while we're looking at IP networks today, there's a number of additional technologies or transports or mediums that we may need to address in the future. Bluetooth, for example, web technologies, all sorts of different ways that we may need to interface with our devices, and we wanted to make sure that we were prepared to be able to address any or all of those as they evolve. Security, of course, is a critical element in building up a media network. As systems are becoming more and more connected, of course, they also open up whole new areas of potential vulnerability. And one thing that's really important to understand is when we talk about security on a media network, we're not only focused on tampering and hacking of the network and the devices themselves, but we may also be concerned with security of intellectual property, theft or hijack of content, injection of unauthorized content. So how can we put together a system that can be secured and encrypted and hardened against those types of malicious actors? We wanted to be able to provide rich support for reconfigurable devices. So if I've got something like a modular DSP system or a mixing console where I'm able to change the configuration, change the types of parameters that are operating within the device, we needed to have a very flexible way to be able to update and adapt the control regime for that device itself without going through a tremendous amount of work for the user. Heterogeneously network capable. In other words, I want to be able to connect to the system how I want to connect to the system. So we provided a number of different network topologies and a number of different connection protocols to be able to support different flavors of connectivity. And last, of course, we wanted to make this an open public standard, something that would be available and adoptable by anybody who is willing or able to get a hold of the specification and use it royalty and license free inside of the development of their products. This really was an initiative that was intended to be for the benefit of the users, the manufacturers, and the industry at large. So, what is OCA? A term that some of you may have heard in the industry or in the press in the past. Well, all of this initiative began back in 2011 when a group of 9 manufacturers from around the industry said, you know what, we've got a problem. We need to address all of those different requirements that we identified as gaps in a control system, so let's put together something that can begin to address some of that. And this began the initiative that we refer to as open control architecture. And this was really the genesis of the technology and of the standard itself. Once we created the initial specification and the initial draft, we then handed this over to the OCA, or to the AES, to begin the standardization process. And this went through their normal track for standardization, and in 2015, it was ratified as AES70. Some good examples of this, of course, are MADI, which we also know as AES10. It's a technology that's been standardized by the AES and brought forward to the market. So, while this was created by the AES, why it was standardized by the AES, and it was developed and supported by the OCA Alliance, we continue today to exist as a non-profit trade association that supports, educates, promotes, and helps develop the standard going forward. So in addition to feeding information back into the standard, we work with manufacturers to help them implement the technology. We also provide a number of tools and resources free of charge on the OCA Alliance technical site. So we offer software reference designs, hardware reference designs, different libraries, different tools, and different utilities that can help people get familiar with the standard and implement the technology into their products as it evolves. So our focus today is really the demonstration, the promotion, and the education of what the standard is, how it works, and how it can benefit products going forward. So let's dig in a little bit into some of the basic elements of what goes into AES70. So fundamentally, we have the specification that describes everything in the technology and all of the subsequent pieces of the spec. We have the class system, which can really be considered to be the heart of AES70 in that this is where the objects of the specification in the device are actually described. And then we have the protocols that actually enable this signal flow to be put onto the wire and sent from device to device and back to the controllers. So let's begin with the specification. It's divided into 3 sections, which we refer to as AES70-1, that enumerates the framework of the standard. This defines the models and mechanisms that actually go into the overall structure and architecture of the standard itself. One thing that's very important to note is AES70 is a control model, not a programming model. When we were developing the specification, we were very clear to draw limits both at the bottom and at the top of the spec as to what we wanted to address. So at the very bottom layer, while we provide objects and classes to describe any type of parameter or object that might exist within a device, we do not dictate how that is actually implemented. So a good example would be a high-pass filter in an equalizer in a device. We will provide all of the names and the objects to be able to describe the filter, the gain, the Q, the slope, all of those different characteristics that you would have for a high-pass filter. But what we do not define is the specific math or algorithm that actually goes into making the filter run. So we just provide a way to actually describe and enumerate that. A really good example that I use sometimes is if I take a MIDI controller and I plug that into a Korg tone module and a Roland tone module, and I hit a C key, I get the same note that plays out of both of those tone modules, but you're getting their own unique samples and their own unique voices from each of the modules. So we don't just define the algorithm, we just define how you describe it and how you can communicate with other devices. Now likewise, at the very top of the specification, we define ways that you can communicate and describe and send this information from one device to another and from one controller to another, but we don't dictate what that user interface needs to look like, or even how that needs to be written. We allow the information to get into the controller, but this is something that can be built up in a command line, it could be built up in a GUI, it could be coded in any number of programming languages. That's really open and completely flexible to the users to implement however you like. So moving on, AES70-2 is the class structure, and as I say, this is really the core of the standard and the spec, in that this really defines the specific objects, parameters, and elements of a device, how those are enumerated, how those are described, and how I can interact with them and control them. Last but not least, of course, is AES70-3. And this is the communication protocol that actually describes how I take this information and put it onto a wire or onto the air to get it from device to device. So let's dig in a little bit to some of these specific elements. Now the framework that we sometimes refer to as Open Control Framework or OCF, this really begins to describe how a device is developed. How do we put together the different objects to actually begin to build up a description of what a device is going to look like? This contains things like instance IDs, specific object numbers for the classes, and how everything is actually assembled and packaged to form a picture or a representation of a device. Now, when a device connects to a controller or to another device, this also establishes a session ID. So I know that I've got an active session and I can actually identify that unique instance of those objects and that sessions within the connection. This is very useful, particularly dealing with converged environments or highly integrated systems. Now, any object within a device is also enumerated with a unique identifier. So I've got an object identifier and then I also have a session ID. And this is how we're able to actually manage some of the traffic management within the system, making sure that the right commands are coming to and from the right devices and the right objects within those devices. Digging in a little bit deeper into AES70-2, or the control class structure, this is really where the core of the object orientation in the standard exists. So this is how I'm describing the guts of my device. All of the objects, all of the parameters, and all of the functions that are residing within a device are covered under the AES70-2. Now, this is a very object-oriented way of building up a class tree. So there's high levels of inheritance, and objects can actually be derived from others. And we'll look at some examples of how these can be built up and how these objects actually look. So with the inheritance, everything is actually derived from a base class that we refer to as OCA root. And then we begin to derive the additional objects and the additional classes from it. And this provides some very unique functionality that we'll talk to a little bit later about how I can address some of those unique device parameters and those very bespoke functions that may exist within a device. Within the specification, of course, all of these classes are enumerated and described within Annex A, and then Annex B also describes the mandatory objects that must be put into place for the functionality of the system to be compliant with the standard. Now, OCC is actually divided into 4 primary categories. We have workers, managers, agents, and networks. Workers are classes that represent signal processing and monitor functions. So fundamentally, these are things that are going to do something within the device. This is a parameter within the device that I can control or an object that I can interact with. So a gain control, for example, would be an example of a worker. Managers are going to be objects within a device that are going to be focused on runtime or housekeeping functions within the system itself. So an example of that could be something like a subscription manager to connect to other objects. It could be firmware, it could be schedulers. Any sort of internal housekeeping function that needs to run within a device can be represented with a manager object. Agents are going to be classes that control flow or are able to actually monitor, read, and report back on statuses of devices. Something like a VU meter or an LED could be an example of an agent, because this is actually going to be looking at the status of a function within the device and then reporting back on it for the user. Lastly, of course, we have networks. So I need to be able to describe how I'm making my connection from one device to another, how I'm actually putting that information onto the network of my choice, and what protocols am I actually using. Workers themselves begin to get even more granular as we begin to break this down. So these can be divided into 3 categories. Actuators will be able to actually interact with an object. You can think of this as a switch or a knob. A sensor is something that will actually be monitoring function on a device. Again, gain, level reduction, status, any type of functions can be looked at through a sensor. And a block or a matrix is a very unique object that we created to be able to support multi-channel devices. An example of that would be if I've got a digital mixer that's actually got multiple parameters, so I could have gain, EQ, aux sends, pans, level control, mute, solo, all of those type of things. What I can do is, instead of creating every single instance of all of those as a unique object, I could create a block that actually contains all of them and then just replicate the block for each channel strip that I have inside of the mixer. So it becomes a much more efficient and functional way to actually replicate all of those and build up my object model. There we go. Just a couple of examples of some of the functions and some of the types of repertoire that we can represent within the standard. Again, actuators can look at all of these different types of interactable devices. Sensors can read back and report on statuses or activities within a device themselves. Now, one other thing that we did within the standard is we created a bunch of strongly typed object classes. So an example of that would be OCA gain, OCA filter. This is an object that is very strongly intended to operate on a certain type of object or a certain type of parameter. But in order to support some of this flexibility in implementing other types of functions within the devices, we also provided a bunch of loosely typed characteristics as well. So if I need something that will just simply operate as a string or a float or a Boolean operator, I can implement those as well and tie those to any sort of function that I have within the devices I need. So it's really flexible for a designer to be able to put in any combination of loosely typed or strongly typed functions And it's also important to note that you are also able to create proprietary extensions and non-standard classes as you need. So what I can do if I've got something that does not fit into any of the standard classes that we provide within the specification, you can inherit and derive functionality from the root class, and you can begin to create your own proprietary class within a device. The really clever thing about how all of this works is it still complies with the standard, but when I do my discovery and enumeration of the device within a controller, I can see the information about that object and what it's able to do, and I can learn how to interact with it. So, just a technical example of this, I can begin to derive a non-standard class from my OCA switch. Within OCA switch, I have an actuator, and then I can begin to add additional functionality or additional features to that specific class. And then I can expose this on the network, and any other device or any other controller, even if it's never seen that class before, can find it and can interoperate with it. So it's very friendly for the developer to be able to describe your own objects, and it's very friendly for the users because we don't need to go through endless programming and translation to figure out how to interoperate with those unique functions. When we get into AES70-3 or the protocols, we have a number of different solutions that are available depending on what is needed for the device. So we refer to these as OCP.1, and we are only using standard transport protocols. For discovery, we're using DNS-SD, which many of you may know as Bonjour. So again, a standard, easily accessible connectivity and discovery mechanism within the specification itself. Within AES70-3, we currently support 4 services. The first one, of course, is TCP, if you need acknowledgement. The second one is UDP. This is handy for very fast data streams, or if you're dealing with hardware constraints or a limited resource device that you're trying to implement this into, a UDP stack can be very helpful. We also incorporate Websockets, and we can secure this by using a PSK architecture if you need to encrypt and secure your data stream. Now, you have the choice between any of these, but obviously one needs to be implemented and supported because we do need to get those objects and get that data stream onto the wire to be able to tie things together. So, the last thing that I really want to dig into here is connection management for AES67, or CM3. Now, when the specification for AES67 was drawn up, it was done, in my opinion, very wisely to be constrained in scope, focused on packetization and audio transport and clocking for how to actually move the information and the audio packets around on the network. But what it did not address was things like discovery and connection management. So within the group that was working on the AES70 standard, we wanted to provide an option that was based on a standard that you could couple with AES67 to provide those discovery and connection management functions within the system. So this really provides a unique feature and a complete set of discovery and connection management tools that you can use for use with AES67 to not only discover the devices, but also nail up and tear down streams and flows and channels between them. So when you combine AES67 and AES70, you have the opportunity to have a fully functional media networking solution that addresses both halves of that picture that I showed a bit earlier. And this, of course, can work alongside any sort of existing connection management regimes or utilities that are already in operation within the media network. This, of course, is in the process of being ratified by the SC0212L Standards Committee. It's already been actually put in place as part of the 2018 specification, and additional work continues to be done on this as well. But we're not stopping there. Within the standards group and within the OCA Alliance, we're also looking at all sorts of other technologies that are out there. So adaptations are being developed and looked at for things like 2110-30, which of course is a subset of 67. Also looking at Dante and potential adaptations to things like Milan to really be able to provide a solution for all different elements of the industry as this standard is adopted and ratified. So I want to just leave you real quickly with a couple of resources that are available for additional information for developers or anybody who's interested in learning more. The OCA Alliance has a website where we have a number of different white papers and presentations on the technology. We also have a newly launched product page that lists and displays a number of different products available on the market today from 11 brands that are supporting and shipping with the AES standard protocol fully implemented. So you can see what's out there, who's adopting it, who's using it. Now on the OCA Alliance technical side, we also host a GitHub site that provides a number of different utilities and tools for anybody who's interested in learning more. We have software designs, reference designs, we have JavaScript libraries, Wireshark plugins, and a number of different utilities or applications that are available for anybody who wants to learn a little bit more about the specification or even begin to try to implement some of it on your own. And when we talk about some of the things that are going to be coming in the future, of course, we are providing a number of different educational and technical resources for everybody. So our work is ongoing within the industry to try to really promote, educate, and support the standard going forward. So with that, are there any questions that I can answer? I know it was a lot of information. Okay, well then thank you all very much for your time. Enjoy the rest of the AES